Welcome back, all of you. So, as per the CIF, a topic was left from the unit number 3. We'll cover up that topic first and then we'll move on to the unit number 4. So, we also need to discuss about phase modulation in brief. We had a detailed discussion about frequency modulation, but as per the course content, we also need to focus a bit on the phase modulation. We'll just have a brief idea about phase modulation and the generation techniques of it. So, as the name suggests, phase modulation, in case of phase modulation, it is a kind of a angle modulation technique in which the phase of the carrier signal is varied in accordance to the message signal. Phase of the carrier signal is varied in accordance to the message signal. This is how we can simply define a phase modulated signal. So if we talk about it in terms of the mathematics, so let's say the carrier signal before phase modulation is a sinusoidal signal, high frequency sinusoidal signal, that is AC cos 2 pi FCT. Let's say this is the carrier signal before modulation, before phase modulation rather. Okay, and the change in this carrier signal after phase modulation would be the phase modulated signal. Obviously the amplitude will remain same, the frequency will remain same, only the overall phase of the signal will be varied. Okay, so this is your phase modulated signal, or you can say it is your carrier signal after phase modulation, right? And this phi is the deviation in phase. This is your phase deviation. It gives you the measure by which the phase is being changed. So this phi of t is nothing but equal to Kp into mt, because the phase change has to be in accordance to the message signal. So this phi of t, the phase deviation, is nothing but Kp times of mt, where Kp is the phase sensitivity of the phase modulator. You can correlate each and every concept with frequency modulation. It is exactly the same, right? So effectively we can say the phase modulated signal can be written as AC cos 2 pi FCT plus Kp into mt. So this is the standard expression for PM. Alright, now assuming the message signal to be also a sinusoidal signal, that is AM cos 2 pi FM t, a low frequency message signal, right? So what about the maximum phase deviation? We have the term that is maximum phase deviation. We know the phase deviation is Kp into mt. This is the phase deviation. What would be the maximum phase deviation? Delta phi. It is analogous to the maximum frequency deviation that will be in the case of FM, right? So delta phi would be equal to maximum of Kp into mt, right? And if you substitute mt as your AM cos 2 pi FMT, so the maximum value of it would be Kp into AM, because the maximum value of this cos 2 pi FMT would be 1. So maximum phase deviation is nothing but Kp into AM. Thus we can say that the standard expression of PM by substituting the sinusoidal message signal would be equal to AC cos 2 pi FCT plus Kp into AM cos 2 pi FM into t. Alright, where this Kp into AM, this Kp into AM is nothing but your modulation index beta, and it is also equal to your maximum phase deviation, delta phi, right? So now you can see one thing over here. The modulation index for PM beta is equal to Kp into AM, and it is equal to maximum phase deviation. This is your modulation index, and this is your maximum phase deviation. Now you can compare one thing with frequency modulation. For FM, the modulation index beta is equal to what? Kf into AM by FM, that is equal to delta F by FM. It is dependent on the message signal frequency as well. But for PM, this modulation index beta is equal to Kp into AM, and it is equal to maximum phase deviation, that is delta phi, and clearly it is independent of the message signal frequency. So we can say that, we can conclude from here that for the phase modulation, beta modulation index and phase deviation are independent of message signal frequency variation. In PM, beta and delta phi are independent of the message signal frequency variations. Alright, so now if we look at the general expressions of the FM and PM, we can have a look at the similarity. Phase modulated signal is your AC cos 2 pi FCT plus Kp, sorry, let us write it in the terms of modulation index, beta cos of 2 pi FMT. This is your simple phase modulated signal, where beta is Kp into AM. Beta is modulation index, that is Kp into AM. On the other hand, the frequency modulated signal, the standard expression is AC cos 2 pi FCT plus beta times sine of 2 pi FMT. Now you can look at the similarity between the two expressions. So the general expressions of FM and PM are almost same, except 90-degree phase shift at message frequency component. So you can say general expression of FM and PM are same except 90-degree phase shift at message frequency component. And clearly the magnitude spectrum of PM and FM is same, so the bandwidth requirement and the power requirement of FM and PM are exactly same. The bandwidth requirement, the bandwidth and the power requirement in FM and PM are exactly same. So the bandwidth of PM would be same, that is that we did with the help of the Carson's rule, that is twice of beta plus 1 into FM, that is equal to twice of delta phi plus 1 into FM. This is the bandwidth of PM, and similarly the power required for PM transmission would be your AC square by 2. That is the power of the carrier and the power of the FM signal. Let us now do a numerical problem based on this. We are given with a modulated signal, a phase modulated signal. The expression is given as 10 cos 2 pi into 10 to the power 6t plus 6 sine 6 pi into 10 to the power 3t. Alright, a phase modulated signal is given as this, and the question is to find all the parameters of PM, and second part is repeat above if the message, rather for the message signal frequency, that repeat the above after doubling the message signal frequency. Alright, so if we compare this expression with the standard expression, we can say that AC is equal to 10 clearly, right? FC, carrier frequency, is equal to 1 megahertz or 1000 kilohertz. FM is equal to 3 kilohertz. This is your FM, and beta is given as 6. This is your beta, and the bandwidth would be equal to twice of beta plus 1 into FM, and that comes out to be 42 kilohertz. All the other values are given here, and PT is equal to AC square by 2, that comes out to be 50 watts. Now if you look at the second part, if the message signal frequency is doubled, that is the FM, which was initially 3 kilohertz, is now made 6 kilohertz. What will happen to the other parameters? What about the bandwidth? Bandwidth will change because bandwidth is twice of beta plus 1 into FM. It is dependent on FM, so bandwidth will also be doubled. It becomes 84K. And what about beta? Beta in case of PM is independent of the message signal frequency variation. We have already seen that. So beta is nothing but Kp into AM. It remains same, which is 6 radians. And PT, that is AC square by 2, that will also remain same since it is independent of message signal frequency, 50 watts. So as the message signal frequency doubles, the corresponding bandwidth will also be doubled. Only the change will be in the bandwidth. Now a simple way to generate a PM signal is with the help of the FM signal. And it's the most commonly used method to generate a PM signal. So we know that the PM signal expression is what? AC cos 2 pi FCT plus Kp into MT. Right. On the other hand, the standard expression of FM is what? AC cos 2 pi FCT plus 2 pi Kf into integral of MT dt. So you can see the similarity between the two. And if one of the signal is known to us, we can easily generate the other signal by some minor modifications. So we can generate PM from FM. Let us see how. We use the message signal MT and pass it through a differentiator d by dt. The resultant would be derivative of the message signal. And further we pass it through a frequency modulator. with some carrier frequency which is obviously required, AC cos 2 pi fct, and we can say the resultant would be the phase modulated signal. Now we can easily correlate this method with these two standard expressions given. So in this manner we can generate the PM signal using the FM signal just by differentiating the message signal and passing it through any of the frequency modulator to generate the PM signal. Because the relationship between the two expressions is clearly seen here, that in FM signal we have integral of the message signal. So if you take its differentiation and pass it through FM, if you take the first differentiation of message signal and pass it through FM, so that differentiation and the integral would compensate each other and will generate a phase modulated signal. So this is a widely used method for PM generation. Let us do one more important question on this concept. Question is given that an angle modulated signal is given to us, that is ST. It is cos 2 pi into 10 to the power 6 into 2t plus 30 sine 150t plus 40 cos of 150t. Okay, so this is the angle modulated signal given to us. Question is find maximum frequency deviation and maximum phase deviation. So in order to find out the maximum frequency deviation and the maximum phase deviation, we'll have to consider this signal, this angle modulated signal, once as a frequency modulated signal and once as a phase modulated signal. So angle modulated signal ST is given, that is cos of 2 pi into the angle, the entire angle, right? So obviously the modulated angle would be phi IT, angle modulated signal, that is equal to 2 pi into that signal, argument of the cos 2 pi, sorry, 2 pi into 2 into 10 to the power 6t plus 30 sine 150t plus 40 cos 150t, right? This is the modulated angle. Okay, this complete, right? This is the modulated angle, right? So now let us consider for FM case, that is a FM modulated signal. Fi, the modulated frequency, would be equal to 1 upon 2 pi derivative of the modulated angle. We know the relationship between F and phi. This is the relationship between. So if you want to find out that this is the overall modulated angle, so if you find out modulated frequency, it would be 1 upon 2 pi derivative of this, right? Substitute the value of this phi I here. So it comes out to be 1 upon 2 pi, and this mind always remember this Fi in case of FM is equal to what? Fc plus your Kf into Mt, right? This is the concept, that the modulated frequency is equal to Fc, which is the original frequency of the carrier, plus Kf into message, because the frequency changes in accordance to the message signal here. So this 1 upon 2 pi, substitute the value of phi I here, d by dt into 2 pi 2 into 10 to the power 6t plus 30 sine 150t plus 40 cos 150t, right? Simplify this derivative, 2 pi gets cancelled out, and we are left with 2 into 10 to the power 6 plus 4500 cos 150t plus minus 6000 sin 150t. This is your Fi, and this is equal to Fc plus Kf into mt, right? Fc is the original carrier frequency, and this is the frequency deviation, obviously, which resulted into a modulated frequency. This is the frequency deviation. Right? We need to find out the maximum frequency. This frequency deviation would be equal to, this is Fc frequency, this is the frequency deviation. It is 4500 cos 150t minus 6000 into sin 150t. Right, this is the frequency deviation. So maximum frequency deviation would be equal to maximum of this term, right? So this term, if we talk about this term, it is of the form a cos 2 pi f1t plus b sin 2 pi f1t, right? And the maximum value of this, I hope you remember, you know the maximum value of this, it is square root of a square plus b square, that you can get very easily by using some trigonometric manipulations. So maximum frequency deviation of this term would be equal to square root of 4500 plus 6000 square, and if you simplify it comes out to be 7500 hertz, and that is equal to 7.5 kilohertz. So this is the maximum frequency deviation, considering this modulated signal as the frequency modulated signal. Similarly, we can find out the maximum phase deviation. For that, we consider the signal to be a phase modulated signal. We know the expression of phase modulated signal is AC cos 2 pi fct plus kp into mt, right? This kp into mt is your phase deviation. So if you compare it with the given expression is AC cos 2 pi 2 into 10 to the power 6t plus 30 into sin 150t plus 40 cos 150t, right? If you compare it with this expression, this kp into mt, which is the phase deviation, is equal to 60 pi into sin 150t plus 80 pi into cos 150t. We multiply this 2 pi in this argument and we get this kp into mt, that is the phase deviation. Now we need to find out the maximum phase deviation. So delta phi would be equal to maximum of phase deviation, that is maximum of this value, and this would be equal to square root of 60 pi square plus 80 pi square, and if you simplify it, it comes out to be 100 pi. This is your maximum phase deviation. So this was all about the phase modulation part that we need to cover up in this course. We'll continue with the unit number 4. We'll begin with unit number 4 from the next lecture. Thank you.